And welcome everyone to the day 3 of SREcon. And as just Luis said, we'll be talking about prioritized load sharing and how you can use flow control techniques to build indestructible applications and achieve fault tolerance and graceful degradation. So first of all, a little bit about us. I'm Harjot Gill, and I'm co-founder and CEO of FluxNinja. It's a startup which we founded in 2021. Recently came out of stealth, based in the Bay Area. And we recently had announced an open source project called Aperture, which we will be covering in this talk in late 2022. And I have a decade plus experience in actually building tools for SREs and serving the community. So across 2 startups, my last startup was Netzel. Interestingly, it was listen spelled backwards. So the key innovation we did there was to how do you go from raw network events and reconstruct protocols and so on to understand microservices and APIs and database queries and so on as an alternative to distributed tracing, like how do you go from low friction approaches. And that startup was acquired by Nutanix in 2018. But by building that startup, we got a lot of insights talking to the practitioners on the ground, really understanding the nature of the failures they face and why do these failures occur, which led us to founding this new company and this initiative. I'll have my colleague introduce himself.
Yeah, morning everyone. My name is Hardik Shingala. I've been working as a software engineer at FluxNinja doing some of the development and operations related stuff. So in general, I have more than 5 years of experience working with the different cloud infrastructure-based applications and development of it. Yeah.
Interestingly, this is kind of our first public talk talking about the project, and hopefully you folks can go to the GitHub and also check it out. So on the agenda, I will first start by understanding the anatomy of some of these overloads and metastable failures on why do applications fail and why do we have prolonged outages, and especially the consumer-facing applications. We'll talk about some of the mitigation techniques, why some of the techniques are less effective than others, and why load sharing makes a lot of sense in achieving fault tolerance. Then we'll be introducing the Aperture project, talking about load scheduling and global quotas if we have time, and also talk about how we dogfood Aperture in the FluxNinja's commercial SaaS solution. The ARC is Application Reliability Center. That's kind of the name of the product we have, which is in early beta testing right now, and do a demo on that. So let's begin. Let's talk about metastable failures, and I'll talk about something called Little's Law. Let's say you have a request serving system. Now it could be a single microservice, it could be entire application, or it could be even a restaurant, right? So you have a typical request serving system, you have requests coming in, and after some processing, you are responding back, hopefully in a timely manner, right? And these kind of systems are governed by something called a Little's Law, which is actually a very powerful law. And what that law says, it kind of defines a relationship between the requests which are in flight, the requests that are incoming, the throughput, and the processing time of these requests. But the key takeaway that I want to on this slide is every service has an inherent concurrency limit, depending on how much you have scaled or Java thread pool or something. There is always an inherent concurrency limit, beyond which your service will become unstable, and you will start seeing a lot more requests getting queued up and a lot of timeouts happening. Very typical, right? This is kind of what's really happening on a service level, and what causes the overloads, right? And let's look at the graph here. What happens during the overload scenarios on a single service is that your availability typically degrades very, very rapidly. As your timeouts, as your latency increases, you start hitting the client timeout thresholds, and beyond that threshold, your goodput basically drops down to 0, right? Now, interestingly, in modern applications, it doesn't really stop here. It usually snowballs into a much bigger failure, usually snowballs into an application-wide outage, and we'll be talking about more about that. Starts with something as simple as an overload on one service, but usually spreads like a wildfire in your entire application, like a chain reaction. And I will be covering some of these failure modes just to give everyone a flavor of how this gets out of control and what really causes this multi-hour outages. So one of the failures that we talk about in the SRE community is a cascading failure, right? So you have an N-tier application with some database, which might be going through some maintenance and some degraded latency, causing a cascading increase of latency across the entire service chain. And sometimes what you could see is completely unrelated failures crop up. For example, let's say you have a circuit breaker configured between 2 services, which might be configured with a very low threshold because it's now seeing a lot more timeouts. It might trip, causing complete outage between service 1 and service 2, complete communication outage, right? So what you're seeing here is like, even though the problem started at a database, it starts manifesting in a completely different part of your application, really alerts going off and people scrambling to figure out what really happened and where, right? The next mode failure I will be talking about is a death spiral, which is very interesting, right? So you have an application like service sitting, and it's a scaled out service sitting behind a load balancer. Load balancer, of course, is doing all kind of health checks on your pods and instances there. What you're seeing is like, as due to some reason, some of the load starts becoming unavailable, right? And what it does is that once a load balancer detects that unhealthy nodes, it starts replacing or like putting them out of the pool, and you start replacing with the new nodes. And by the new nodes take time to get ready, or you're talking about passing readiness checks, service discovery, and so on. And while you're doing that, the load shifts to the remaining instances, which also start becoming unhealthy with the new load. So you start getting into this kind of a death spiral mode where one by one your instances start going offline, causing a complete outage and very hard to recover from. Now let's talk about something called a retry storm, which I think a lot of you might be familiar with. This is something we see very, very commonly across a lot of the conversations I've had over the years. Going back to the same example, like you might have a database experiencing high latency, and as your latency increases, it starts like propagating down the chain, causing timeouts in the end client and causing retries, which exert even more pressure on the database, right? But I want to zoom in a little bit into this scenario. Now, this is kind of a typical graph of like what a retry storm looks like and why these failures are very hard to recover from unless you're like doing some sort of manual intervention or some sort of intervention. So let's say you have like a capacity of like 1,000 queries per second, and usually your load is less than the capacity, like maybe 600 QPS. And temporarily, you might have like some reduction in capacity. Maybe you're doing some maintenance on a DB, or someone ran like a very heavy query on a database, right? It could be due to many reasons. And you had a temporary reduction in capacity causing like just a slight overload. And what happens after that is like you start seeing a lot more retries happen and your load increases. Now, the interesting point I want to make here is that even if you, let's say, restore the capacity to the original levels, let's say 1,000 QPS, and you still have the same number of clients, interestingly, you will still be in the state of permanent overload. Now, this phenomenon and these kind of failures are actually called metastable failures, right? So this was from one of the presentations we saw in another USENIX conference, I believe, where this kind of the state transition, like you have an application which in the normal circumstances is stable, but once you slightly start increasing the load, it becomes vulnerable, right? So you don't have enough protections or flow control, or giving an analogy like a seat belt on a car, right? And if you like push a little bit further, like it pretty much goes over the cliff. It goes into like a positive feedback loop, kind of a snowball effect or a self-sustaining effect called a metastable failure, right? And now once you are in the metastable failure, it's like self-reinforcing, right? So without some sort of intervention, it's impossible to get out of their bad state. And this is what typically causes like crazy outages on, let's say, Black Fridays, or or like on like you had this Slack outage on like 2nd January, like people coming back and opening laptops at the same time. And once everything is in that bad state, you have to just switch everything off and slowly bring your services online, causing really a multi-hour prolonged outage. Now, interestingly, like these outages start with very, very common triggers. Like, and you might be familiar with a lot of these triggers, like starting with insufficient capacity allocation, like you have Black Friday. For example, Costco going down on Black Friday was due to this, like you didn't like provision enough capacity, causing cascading failure. It could be like performance regressions because you just shipped a new version of your service which has a performance regression, causing a cascading failure. It could be some, interestingly, like we talked to a few customers who had unexpected traffic spikes because some of their sales campaigns went viral, right? Or like if you're a digital media company, maybe some of your articles that you're posting have gone viral, right? And that also causes like cascading failures, right? For example, Hacker News starts seeing a lot of these outages where they have to log out users to protect the application. Now, interestingly, now that like we're building on like open source technologies, and we're also building on like Amazon DynamoDB and cloud components, a lot of the time slowdowns in those third-party components also cause cascading failures in your application, right? So if you look at any modern applications today, you're piecing together different open source technologies together or hosted services, right? So even those become a source of these failures. And these failures could even start with something as simple as like a cache problem. Like you could have like a cache which has gone offline, causing the load to shift to the main database and causing a cascading failure, right? What I want to like point out here is that these failures have been there for like decades, like, but those used to be like black swan events, unpredictable and rare. But with modern applications, they have actually become much more common. Now, as you adopt microservices or even any cloud application, as I said, like you're using open source technologies and hosted services, the surface area has multiplied. So you're seeing these failures on a very, very common basis, and something has to be done about this, right? And this is where I will like start by talking about some of the mitigation strategies. So typically, like we've seen local countermeasures in the wild, like starting with something called circuit breaking, which a lot of you might be familiar with, like typically implemented in a service mesh like Envoy or Istio. And what you're seeing is like a localized view between service instances. Let's say you see high error rates, and after a certain error rate threshold, you will trip the circuit breaker, causing a complete communication breakdown between two services in order to protect the services, right? And the problem with this approach is that even though it does protect the services, but I found very few teams have been able to actually configure it accurately, because the tripping threshold is, some services just a lot more tolerant to errors while others are not. And it's a very client-side technique. It has no awareness of your failure maybe started in a different service altogether. So there's no global awareness here. Then you have static rate limiting. A lot of people actually put rate limits on per users, which is great if you want to like prevent abuse or enforce some business contract. But this technique itself is not great for protecting services, right? And you have seen like how ChatGPT puts like limits of 25 messages every 3 hours. Those kind of techniques are like kind of like an art. Like there's no science behind it. Like you have to just figure out some threshold where your service is protected, and it's very hard to figure out these limits, or even like waiting rooms and so on. The other technique we see like typically is like reactive autoscaling. Yes, a lot of people like autoscale based on a cron job beforehand, based on the capacity needs or predicted capacity needs. But if you're like, let's say, doing it in a very reactive manner, it's very hard. Like especially like if you have stateful services, you're talking about like Kafka, for example, or something, like you start resharding, right? And even if it's stateless services, it takes time to like hydrate those new instances. You're talking about Java application coming from a cold start, doing discovery, setting up database connections, and so on. And interestingly, the bottleneck typically shifts elsewhere. So you start by scaling one service, bottleneck will now shift to another service, and so on. And another point I want to make is it's not very cost effective, because a lot of the time the traffic spikes you might be seeing are temporary. So it doesn't make sense to like provision like crazy amount of capacity just to absorb any kind of transient spikes, right? So the local countermeasures are not very effective right now. That leads me to looking at adaptive load shedding. Like what is really effective, and what we've seen with a lot of web scale companies like Google, Netflix, and they've all done it, actually even LinkedIn, is you want to like shed excess load, like model Little's law, figure out like what's the concurrency limit of a service and so on. And when you're exceeding that limit, you want to like shed the rest of the loads in order to protect the service in a smart way. Interestingly, unlike circuit breaker, you're not like switching off all communication or API calls. You're like letting it just enough in order to not crash the system or keep it stable. And this is kind of a typical graph if you have adaptive load shedding in place. Now, what you will see is that your availability in this scenario degrades much more gracefully, much more linearly, right? As your latency increases, you don't have like that sudden cliff that we saw in the earlier graph. I mean, it's this graceful degradation in a way. Now, I'll basically like exchange some of the design notes that we have taken, like on what does it take to build this kind of a system. Like let's say you were thinking of building a protection in-house. So the requirements for building adaptive load shedding is like, first part is like, how do you model the capacity on application? Like how do you find the ideal load in a constantly changing environment? Your instances, you have like auto scaling, you have churn in your instances and so on. So if you have like capacity which is like too low, you might have wasted capacity, you're like leaving some capacity back on the table. But if you're too aggressive, then you can end up with unresponsive servers again, right? And interestingly, like it's great. I mean, if this system could be designed on the foundations of observability. So over the last decade, what we have seen is like rapid innovation happening in the observability space, thanks to a lot of the open source efforts in Prometheus ecosystem, open telemetry, and so on. So the idea is like, how do we think about building a layer of controllability as the next step on top of observability that we have invested in the last decade? Like this brings me to the point that we have to start thinking about how do we bring ideas, which is kind of a lost art, like from industrial control systems like PID controllers. First of all, like how many are familiar with the PID controller here, like proportional, integral, and derivative controller, right? So if you have like driven a car with, like, let's say, adaptive cruise control, that's a PID controller. Like, you're maintaining the distance between the car in front of you, or even Tesla autopilot, like a lot of it is actually a PID controller in addition to machine learning they do. And then in addition to that, you have to start thinking about active queue management algorithms. Like, you're talking about TCP, BBR, some of the techniques that we have seen in networking where you could do modeling-based approaches for doing congestion control, estimating the capacity and the bottlenecks, and doing flow control, right? And AIMD, CodeL, so all are great techniques to think about. And the last point I want to make is, like, when you're thinking about building a load shedding system, like, you have to start thinking about how does it interact with other control systems with similar goals. Like, these cannot be independent systems. They all have to be connected together. Because if you have load shedding in place, your autoscaler might be oblivious to its presence. So you're doing load shedding to protect the application. Autoscaler may not even see the signals. If you're looking at CPU as the signal to autoscale, you may not even see CPU go bad if you have autoscaling in place. And if you have, let's say, like a multi-region load balancing, again, you might have similar issues where you might not see saturation increase in one of your regions and so on. So all these systems have to be tied together in the future, right? So that's what kind of like, what does it mean to like add a layer of controllability in the future cloud applications? So first of all, closed loop automation, right, as opposed to runbook systems that we typically talk about. This is not event condition style, action style automation. This is more like continuous tracking deviation from your service health state and then bringing the application back into a stable state. The next thing I want to talk about is, like, we don't want to be savages. Like, we don't want to like drop these requests on the floor just like that. We want to think about prioritization and scheduling, right? So if you have a web application, most of the times, like, you have some business API calls which are more important than others. Let's say you are an e-commerce website, maybe doing ability to do a shopping cart checkout is a feature which is more important than, let's say, showing recommendations to a user, right? So you want to be able to then schedule these API calls as your system is running out of capacity. How do you think about token buckets, weighted fair queuing, and those kind of techniques, or even probabilistic dropping if you don't want to like use a queue, and fairness algorithms in order to like prioritize these API calls, right? And another topic I will talk about is, like, what is going to be the definition of tokens in this kind of a system? Like, if we go to the definition of Little's law, the tokens could be your estimated latency, because if you're talking about queuing from the networking world, your packet size is the cost of transmitting a packet, but in the world of APIs, you have to estimate the latency of those API calls and then do the scheduling based on that. It could be even query complexity, right? If you're, let's say you have a GraphQL service, you could like figure out the complexity of the query of admitting a request and then schedule based on that. Or if you're, let's say, talk to a third-party service, let's say OpenAI, like everyone's talking about generative AI now. So their definition of tokens is very different. So they rate limit you based on tokens in your prompt, right? So you could be scheduling and working backwards from their limit to prioritize APIs to OpenAI, right? So this brings me to the Aperture project. Now, this is what our team has been working on and building for the last year and a half, like roughly 20 people in stealth. And so a lot of these ideas came together in the Aperture project, so which is kind of the first open source platform which provides this observability-driven load management. And the platform is programmable through a declarative policy language, which is interestingly expressed as a circuit graph. So you could take like signal processing components, stitch them together to build your automation logic here, or the closed loop automation logic. And in addition to that, like our team has worked hard on like generating high-level blueprints for common use cases. So you have a lot of this programmability, but for a lot of common use cases, we provide like high-level blueprints that you could just use and configure in the system. And we kind of like wanted to build this on the shoulder of giants. So basically, we layered this as a add-on stack on your existing infrastructure. So we have invested in building SDKs. So think of like Java interceptors, middleware interceptors, just like what you do with open tracing to get traces out of Java application. Like we just basically built upon the open tracing libraries to do flow control in addition. Then we also like work with like service mesh in Aperture. Like, so if you have Istio or Envoy, so basically we're leveraging authorization API. So instead of doing authorization, we're doing flow control. And then in addition to that, we also have done some plugins for gateways and proxies like Nginx and Kong. So this is kind of like a high-level architecture of how Aperture is inserted into an application, right? So you have a control plane and a data plane. So your data plane is an Aperture agent, which is a sidecar kind of next to the application, either a daemon set on a Kubernetes node. I mean, if you're using Kubernetes, or it could be a sidecar in the pod. And the way it's interfacing with the application and the service is through SDKs, through service mesh like Istio, Envoy, or gateways. And that agent provides kind of like a flow control as a service. Think of it as a flow control system, or like you're basically putting a seatbelt on a service by installing this agent next to the service. And the brain of the system is a Aperture controller, which is hosted, it could be in a separate cluster, and that is the one that's like doing constant observability and completing the feedback loop by constantly dynamically programming the agents to do flow control. So all the requests in the data plane are like served by the agent in a very low latency, right? So most of the feedback loop is like periodic feedback loop, takes multiple seconds, but that's like completely in a separate server through etcd and Prometheus. So I'll talk about like adaptive load scheduling and what does it take to like build service protection based on a feedback loop. So this is what we want to be able to achieve. Like let's say you have a multi-tier application, you have like database, third-party database or something. You want to be able to like observe issues in a database. Let's say your number of concurrent connections, you're running out of connections on a database as one signal and so on. You could be looking at latency, multiple signals to get confirmation, right? And then based on these observations, once you have made like enough confirmation that overload has happened, you want to then actuate by, let's say, you want to like start scheduling the APIs at the gateway itself, so there is no wasted work in the service chain. So you're like detecting the problems much further up, down, it's upstream, I guess, right? I mean, some people just keep changing these terms, but you want to like start actuating downstream. So this is what a policy in Aperture would look like to achieve this, right? So this is what we want to achieve. This is kind of a visualization of a graph of what the YAML configuration would look like if visualized as a mermaid diagram. So what we're doing here in this very simple policy, like we are running like a Prometheus query on latency. I mean, this is, by the way, one of our simpler policies where you are running a Prometheus query on latency and then making it go through an exponential moving average so that you kind of establish like a historical baseline or what a normal latency looks like. And based on some tolerance, you are configuring a controller, which is like looking at the deviation between the set point, which is your long-term average latency, and the real-time latency. And based on the deviation, it does adaptive load shedding, right? This is a very high-level policy, but this is kind of what a single component looks like in a YAML format for this policy, very high level. So the policy is kind of a circuit composed of multiple components, and the signals is what like flows between the components. So you have each component, you can have like input signals and output signals. In the case of adaptive load scheduler, you have like a signal and a set point coming in, looking at like deviation and so on. And in addition to that, like we have some of the workloads defined where you could like mash your API calls against some labels in the traffic. And I'll be talking more about these labels, like what these really are, and do prioritization based on that. For example, in this example, like we're looking at two workloads, like guest users, which are logged out users, and subscriber users. And let's say in case of an overload, you want to give subscriber users higher priority than guest users. You want to let them into your application, maybe like much more frequently than your guest users, which can be dropped. Then you have a selector on which service do you want to deploy this policy, on which agent and which service this policy applies to. Just to give you a flavor on what like the programming language looks like. Now let's talk about the insertion, like what's happening in the data plane, right? So you have a service, you have requests coming into a service and responding back. And for each request that's coming in, so your service is talking to the sidecar Aperture agent and getting a decision from the Aperture agent. It's just like an authorization decision. So instead of authorization, we are like asking for a flow control decision, whether this request has to be rate limited, concurrency limited, sampled, and so on, because there are like multiple use cases that Aperture provides. And once the request is sent to Aperture with all the request payload, the headers, so what we have done is like built on inbuilt Rego. So if you guys are familiar with open policy agents, so they have a language called Rego, which is really great for taking like extracting information out of your structured data like JSON, right? So you could like start labeling your traffic based on let's say JOT tokens or some attributes in the payload. And interestingly, those attributes that you extract from a request are actually your open tracing baggage. Now this is the interesting part. So we are using the same technology that we are using for tracing and observability to do control. So the same headers or the baggage that you are inserting as a context of a trace is actually used for flow control. So you could take the same labels, use those for rate limiting, for concurrency limiting, and so on. Then after the classification stage, we have, let's say, a scheduler, which makes a prioritization decision on whether that request is allowed to go through or does it have to wait until it can get some tokens, right? And the baggage is propagated to the next service. So you could even like classify somewhere in your service chain and actuate somewhere completely if you're doing like baggage propagation. Now, let's talk about prioritization. So a lot of times, like, you have a service which is shared, like in this example, like let's say you have a checkout service which is getting invoked by your shopping cart, search, and inventory, and all these client services are not equally important. Like you want to like be maybe your shopping cart checkout is more important than being able to search and inventory, right? So what you want to be able to do is like, let's say if your checkout service is overloaded, you want to give like a lot more bandwidth to the cart service here. So what we're doing here is like we actually built a weighted fair queuing scheduler inside the Aperture agent, which classifies the request and then based on the token bucket. By the way, this token bucket is configured by the controller. So based on your observability data, so the controller figures out how much load can the service take and adaptively schedules, which is pretty cool. Now, based on the service health signals, you are looking at how much a service can take. And if it cannot take all the requests that are coming in, then it smartly schedules the requests. So bringing in a lot of the ideas we have seen in like operating systems and networking into the API layer. So think of Aperture as kind of like a scheduler for your APIs, pretty much. So we may not have a lot of time to like discuss global quotas, but so we have like another technology like which does like precise counting of requests, because the technique that I mentioned earlier was based on service health signals, but sometimes you may have a scenario where you have precise quotas that you want to like allocate between services. Let's say, as I give you an example, let's say you Amazon DynamoDB, they only allow you to do certain requests per second to their service. Now you have to work backwards from that limit and schedule at your end. Think of it as client-side rate limiting. Like that's kind of another way of putting this thing, right? So then how do you do this precise counting, right? So the precise counting, like we can actually build kind of a distributed hash table. So these agents actually are talking peer-to-peer among themselves and sharing like this global, these token buckets and are then distributed in the cluster itself. And within the cluster itself, like we are able to coordinate exact counting of these requests at high performance, like as compared to, let's say, Redis-based approaches and so on, and then schedule those requests. So that's another technology that's available inside Aperture agents, like precise counting and global quotas. So what I will do now is like hand over to my colleague Hardik here, and he will talk about how we are like testing Aperture. Like one of the best ways, as you know, is to, if you're building a product, is to dog food it. So we have this like commercial product, FluxNinja Arc, which is a SaaS service, and that's where we kind of like use it as a test bed as well to test Aperture project as well. And one of the things we are doing in that setup is how do you schedule GraphQL APIs by looking at health of a PostgreSQL database. I think over to you.
All right. So as Harjot has already explained about the Aperture's capabilities and what problems it is addressing, let's see it in action with this demo, right? So in this demo, what we are doing is we added the Aperture in the FluxNinja Arc to monitor the Postgres as instance, right? So let's see the underlying architecture to understand like what things we are doing over here and how we are handling the things, right? Yep. So if you see over here, so we have these two key services, the API service and the agent service. So the agent service is responsible to collect the metrics like the heartbeat and the other like useful details from the agent and controller running like in different Aperture instances. And the API service is responsible to gather the information requested by the UI from the end user, right? So both this agent and API service hits the Hasura with the GraphQL queries to fetch the details from the Postgres, like it could be fetch or the like store details, whichever they need, right? So in this case, like let's see how Aperture is included into that. So if you see, we have these two policies defined over here, right? So the first policy is the auto scaling policy on the Hasura. So what it does is like whenever a request is received on the Hasura, Aperture monitors it and collects the information like the flux meter, which is the workload latency of each request coming to Hasura, right? So in that it says that if there is a spike in the latency, like suddenly the latency started increasing, then it starts like scaling out the Asura so that we can mitigate the issue if the Asura is being the bottleneck over here and it is blocking the traffic due to the capacity allowed on the Asura, right? So apart from this, we also have a classify defined over here. So over that, we are using the OPA as Harjot mentioned, right? So in that, we are getting two additional labels. One is the source, like the source of the request from where the request is coming to the Asura. And the second is the operation type. So we are parsing the GraphQL query in the OPA, like Open Policy Agent Rego, and then we are getting what is the operation type level, whether it's a query operation or it's a mutation operation, right? And based on that, we are detecting if the API service query operations are getting like higher latency, we start scaling out the Asura so that we remove the bottleneck of the Asura, and we can be sure that the Postgres is being the bottleneck over here, or Postgres is facing the performance issues, right? And that is handled in the second policy. So the second policy is the service protection policy, where we are monitoring the Postgres use of CPU percentage and the maximum connections used, right? So what we do as a primary signal, we take the maximum connections used, like if it is greater than 70%, we can say that it might be under overload, right? But that's not always the case, right? Because sometimes there are some unused open connections, like the client didn't terminate the connections properly and we ended up getting a lot of open connections, right? So as a secondary matrix to confirm that the overload is correct and it's not a false positive scenario, we also take the CPU usage percentage. So if the CPU is also greater than 70%, we can say that, okay, Postgres is under overload because both of these metrics are getting a high value, right? So to get the metrics from the Postgres, like a user don't have to do anything or do any additional setup. The beauty of the system is like they just need to do a configuration on the Aperture policy, and the rest all things are being handled by the Aperture agent itself. We use the OpenTelemetry collectors for that, and that is being handled by the agent itself, right? So now we got these two metrics and we confirm that the Postgres is under overload. So now what happens if we want to do some workload prioritization? Like over here, the API service is being directly hit by the UI to fetch the details from the end user, right? So our effort is to like get the minimum effect on the end user when the overload happens, and the agent service is being called by the Aperture like every couple of seconds to send the heartbeats and all the details. So even if we miss one or two iterations of that, it's fine, because when it sends the next heartbeat, the things will be corrected again, right? So for this case, we are giving 255 the highest priority to the API service, and then we are giving a second layer of priority to value equal to 100 with the agent service and the operation time equal to mutation. So the reason behind doing that is like before doing a mutation call from the agent service, it does a set of query operations also, right? So if agent service has reached to a level where it is doing the mutation, so some work is already being done by the agent service, and we want to take it to the completion instead of breaking it from here and then again starting everything from the scratch, right? So that's the reason we are giving it the second priority, and then the last one with the agent service as a source and the query as a operation, right? And so let's see what happens when the Aperture is not in the picture in this case, right? So if you see during this time when the load is normal, so over here we are using K6 as a load generator. So we are giving a set of virtual users with constant sending traffic to the agent and the API service, so that we can do the warm up. Like when VU increases rapidly, we can see that okay, there is an overload or not, right? So if you see in this case, the latency normally stays around 10 milliseconds, 6 to 10 milliseconds. But as soon as the overload starts, the latency spikes up to more than 250 or 300 milliseconds, right? So at that time, both Asura and Postgres both are under overload, and they are not able to meet the capacity on which the requests are coming, right? So on the other side, if you see the acceptance rate when the load is normal, it is higher, like we are accepting 100 requests per second from the API service and similar to the agent service, right? But as soon as the load increases, we should be seeing a spike in the acceptance rate, but opposite to that, we are seeing an exponential drop in the acceptance rate, because the system is not able to serve the request it is getting, and eventually all the things are getting slowed down, right? So this is without Aperture, and let's see it in the live demo, what happens if we have the Aperture in picture, right? So over here, if you see, initially the acceptance rate is similar to the previous diagram, but as soon as the load increased, there were some spikes in the latency, which is like sawtooth pattern which we are using over here. So whenever there is a spike, Aperture tries to mitigate it and gets it back to the normal and continuously tackles the things, right? So over here, if you see, like the blue line is of the API service. So you can see that as it is having a higher value in the terms of the priority, the acceptance rate is always higher for that, and the acceptance rate for the agent service decreases because it's a lower priority request, and our try is to solve the API service the maximum, right? So, and yeah, if you see, there will be some rejected requests, like the query request is getting rejected at the highest because that's having the lowest priority on the system. And as the query request is getting rejected, the agent service won't reach to the level where it has to do the mutations, right? So that's why the mutation is lower on the acceptance rate also, and it has to drop some of the API service requests also to keep the system in the steady state, right? So it is possible that if you don't want to do any traffic drops on the API service, you can exclude it from the load scheduler. So the request won't get scheduled, and it will like always get accepted, and the request only will be monitored with the agent service. So it will try to keep the API application held with the agent service only, right? And yeah, so this is the auto scaling graph. So if you see, we have started from the value 1 as a Hasura pod. And as soon as the latency started increasing, we started scaling out the Hasura and to the maximum value 10, which we have given in the policy, right? So if in between, if it sees that the latency is back to normal, it starts doing the auto scale out automatically. So the user don't have to worry about configuring those values. Based on the latency, the system will automatically do the scale in and scale out to keep up with the requirements. Because deciding what should be the actual scale is a bit difficult, on what conditions you need to scale out or what conditions you need to scale is a bit difficult part, because you need to understand your service, you need to understand what are the load requirements or what are the load capacity of the system, right? So that is being handled by the Aperture very, very intelligently over here, right? And yeah, so if we see over here, this is the diagram where we are monitoring the maximum connection usage, right? So if you see over here at this particular time, we have started seeing the overload where the CPU percentage, the max connections went above 70%, right? And at the same time, you will see that the connection or the request management started, the request scheduling started. But as soon as it goes back to the normal, Aperture starts accepting all the requests back to normal, and it says that okay, application is now normal. I can accept more requests as it is coming from the end the users, right? So as Harjot has mentioned, there is a circuit diagram, but as a user, people might feel that it is hard to design that circuit, or they might not know each and every component, right? So to overcome that, what we are doing is we are packaging a lot of blueprints with the setup. So where you just need to provide a basic configuration YAML file, and based on that, the entire circuit will be generated, and using the Aperture CTL, the CLI tool which we are giving, it will be directly applied on the Kubernetes cluster, or maybe in the non-Kubernetes setup also, where the Aperture is running as a Docker instance or something, right?
So we use JSONnet to generate these policies. So there's a policy language which is highly programmable, allows you to do this pretty cool global control, picking up signals from one of the services, actuating to other services, and doing all the signal processing in between. And on top of that, we have written generators which take JSONnet YAML, and then using JSONnet, we are able to generate those policies for you.
Yeah, so if you see, this is the values file which we are configuring to the workload prioritization, right? So you just need to give a Prometheus query, the side point, the maximum limit where you expect that your service will be working normally. Then you just need to define this much details to get the Prometheus Postgres metrics into the system. You don't have to do any other setup. Just define these details, and all the metrics will be pulled from the Postgres into the Aperture Prometheus, where the agent and the controller will be monitoring it, right? And then yeah, you can use these things to define the workload priority, what should be the priority for each request based on the labels which we are getting.
Can you show the labels at Rego up there?
Yes.
This is the way we're getting.
So this is the Rego which we are using. So we are getting the source from the headers which we have, and we are parsing the GraphQL query to get the operation type, whether it's a query operation or it's a mutation operated. And similar to the auto-scaling one, you just need to define on which particular deployment the auto-scaler should be applied, what's the maximum value of the replicas and what are the minimum values which you want to maintain in the setup.
Yeah, so the cool thing is pretty elegant, you're doing very sophisticated control, scaling, scheduling, rate limiting, so even sampling, feature flags. So you could actually do feature flags with Aperture or server-side feature flags, all in the same system, all kind of load management.
Yeah, the same diagram which I just explained, with the Aperture, the things are in the check. Service is always healthy, so yeah, you don't have to worry about the reliability of the system.
So that's cool. And yeah, we're happy to take questions. I know we are 5 more minutes of speaking time, but happy to take questions now.
Yeah, you can scan this QR and reach out to the Aperture repo, and star us so that we can get some love from the community.
Yeah, by the way, it's Apache v2 license, so very permissive.
Thank you.
All right. Thank you.